name is Marcellus Bronner, and I am your moderator today. I'm pleased to introduce you to my colleagues who will take you through this journey and present you today's webcast. With me are Mike Lawton and Marv Wagner. I'll provide you a little bit of background information of the two. Mike Lawton is the lead product planning engineer for R&D business within the mobile broadband operation at Agilent Technologies. Mike began his career with HP Agilent in 1992, working in HP laboratories in Bristol, UK, working as research engineer on a variety of wireless projects. In 1998, Mike moved to Ipswich and joined the fiber optic product division, where he held positions in both product and strategic marketing. In 2005, Mike moved to Edinburgh to take a marketing position within wireless test. During his career, Mike has been awarded 4 patents in the areas of wireless networking and fiber optic communications. He has also represented Agilent and served as chair for external groups developing both industry standards and multi-sourcing agreements. This is about Mike, and now introducing Marv Wagner, who is our wireless applications engineer for Agilent Technologies mobile broadband operation. He has instructed customers on methods and tools to test cell phones and data modems through all phases of development and manufacturing. He has authored numerous application notes and technical presentations to improve the efficiency and effectiveness of mobile phone test. Marv holds a Bachelor of Science in Electrical Engineering from the University of Utah. He has worked for HP and later Agilent Technologies as an RF hardware designer, application developer, and R&D project manager for development of Agilent's wireless communication test sets that are using for developing and manufacturing mobile phones. He currently lives in Spokane, Washington. We will begin our webcast in a moment. First of all, I want you to make familiar with the system. For everyone's comfort, this is a lecture-style meeting. However, you can send questions to Mike and Marv in writing at any time during the session through the Q&A window of the WebEx meeting. Mike and Marv will answer your questions at the end of the session. In the Q&A window, be sure to select all panelists before sending the question. While the answer to your question may be published for others to see, we will keep your identity private. Please be reminded that this webcast will be recorded, so you can review and share with your colleagues at any time. And now I'm passing over to Mike. Welcome, Mike.
Thank you, Marcellus. And hello, everybody. Welcome to today's webinar entitled 10 Steps to Determine Your 3G, 4G IP Data Throughput. As Marcellus said, my name is Michael Lawton, and I'll be presenting in the first half, and then I'm going to pass along to Marv Wagner, who's going to talk through some real-world measurement he's done for IP data throughput. So here's an agenda for today's talk. I'm going to start with a brief introduction to talk about some of the key market drivers and how that relates to approaches to measurement, and in particular, the importance of the end-to-end IP measurement. I'm then going to go on and spend a little bit more time talking in a bit more detail on the end-to-end IP measurement, and I'm going to build up a sort of model of complexity where I start with a simple approach and then add complexity to get to the sort of ultimate in end-to-end IP data throughput measurements. And the approach here is really to show how with the layering of complexity you can use end-to-end IP to make a very, very useful measurement, and then you can also use that model of complexity to peel back what's happening to maybe get further into the debug of your designs. And then with Marv's real-time results or real-world results, we'll have a look at how you can do that peeling back of the onion. And then we'll complete with a summary. Okay, so this slide is the technology drivers, which I think we're all getting quite familiar with these in the industry, I think, but clearly high speed and more data is a thrust that is very self-evident in our industry. In recent years, there was a focus around voice and capacity, but we've moved on from that now, and we're on an explosive path in terms of increasing the data rate of systems as we support more and more data services with cellular networks. And whilst the headline is all about speed, it's also low latency that helps to support that high speed being useful to applications. So if we look at what's happened with latency across the systems as more and more developments have taken place, we've seen that come down from several hundred milliseconds to a little bit more than 10 milliseconds now with LTE. So very high data rates, very low latency is important. And then I guess the other overriding thing that we've seen that probably is throughout the whole of the telecommunications space is a real dominance of IP networking. Pretty much every piece of traffic now that's moving around the network is dominated by the use of the IP infrastructure. And so that's an important thing that we need to address in wireless networks. And I guess that moves me on to my next point, which is around convergence. LTE and IMS are both technologies which the radio world is converging around. For both 3GPP2 and 2GPP, the next generation of radio access technology is LTE-based. And they are also both moving towards an IMS-based architecture. And both of these technologies are fundamentally based on IP-based approaches. So we can see the importance of IP there. And then finally, I think it is worth mentioning that interworking is and remains a very important driver in our industry. It's expensive to roll out networks, and so the way to, most operators want to make good use of those investments, and so it's important that new technologies can interwork with legacy technologies, A, to provide seamless coverage early on in the development of the technology, and B, to make use of that infrastructure that's already out there. That brings handover requirements. But I think you can see from what we've talked about there, IP is and throughput is an important part of these drivers. Higher speed, lower latency, all IP, use of IP-based technologies. So end-to-end IP and throughput testing is a key performance test now, and I think it's going to become even more so as we move forward into the future. So one more slide on the market stuff before we get through to talking about end-to-end IP. This slide really I've just got to sort of highlight, if you like, the importance now of data versus voice. So this is the data curve for the amount of throughput on cellular networks versus the voice curve here. And we can see that voice, whilst it's still a very dominant application, it's not now governing the dominance of the traffic. It's voice that's doing that. And we're now at, we've reached the 1 exabyte in terms of traffic moving around networks. And that's 10 to the 18 bytes. That was a new unit to me. So clearly the amount of traffic from a data perspective is huge, and it's still growing. And so we need to find ways to make sure we can accommodate that. And the technologies themselves, they are increasing their line rate to try and address that need. You can see it wasn't that long ago when we were talking about WCDMA at 384 kilobits per second, maybe around the early 2000s. HSDPA, I remember doing testing on that in around 2005 at 3.6 megabits. Well, now we're up at 100 megabits, and there's 1 gigabit being talked about by the next generation standards. So we're definitely seeing explosive growth in the line rates to support this need for more and more traffic. Okay, so I mentioned about IMS. I just want to make a couple of comments there. I think if we look at legacy technologies and the way we use phones today, it's quite clear that we essentially have vertical stacks for our different services. We have a voice signaling path where you set up a circuit switch bearer. We use a signaling plane to support SMS. And then we have a packet switch bearer for IP. And when LTE first started to work its way through the standards arenas, it caused a bit of controversy, by essentially saying it was just going to create a packet switch bearer. It wasn't going to create a circuit switch bearer for voice, and it was going to run SMS through the packet switched bearer. And I think for many that seems strange, given the importance of voice to telephony. However, now as we look at this, I think it's become clear that what we're enabling by going down the IMS approach and a focus on everything working on the packet switch bearer is we're now able to take all of these individual applications which you used to have to use in isolation, and we're able to incorporate them into a single communicating app. So users of the phone will be able to talk whilst at the same time maybe sharing a web address through chat, or sharing a file and doing a file transfer, or even sharing location information. So it's clear that that's an experience that will be richer than having to work between these different apps, which is what you typically have to do today. So I think when LTE went for the packet switch bearer only and the support for IMS, it was actually a good long-term position which will help support usability going forward. And of course, it reinforces the topic of today's conversation, which is all about end-to-end IP. So let's move on from the introduction and start to think now about some different ways of doing testing. Now, I've written down here two traditional testing techniques. One of them, physical layer testing. Now, this is an approach where you, in essence, try to simplify the testing in order to focus on the lower layer and also focus on the RF implementation. So you might remove the need for the signaling associated with call setup, remove the need for sending data at the top of the stack, and simply send test data through the physical layer of the device, and then test the receiver's characteristics, test the transmitter's characteristics, and really ensure that you have a good physical layer implementation. That's very, very valid and very useful testing, and obviously it's often done at the early points in the life cycle during a design. Moving beyond that, as a part of the design process through the industry, there are standards-based testing which have become well accepted as a kind of conformance requirement, which is an acceptance level that operators typically insist on as a baseline. They often want more beyond that, but this set of testing is very valuable and very consistent as a baseline across the industry. So the 3GPP generates standards, and then organizations such as the GCF work to administer certification and validation capabilities which allow devices to then go through a set of pre-described testing to make sure they meet a certain set of capabilities and performance levels. So as I mentioned, that's very well used and accepted throughout the industry, but it isn't the complete answer in terms of testing. None of the testing actually requires an end-to-end IP connection today. I think that will change in the future, but right now it's mainly radio focused. And most of the testing is associated with an ideal environment. And you'll see in today's talk, when we build up complexity, we're going to talk about doing testing in more of a real-world environment. So it's very, very useful, and it creates a good baseline, but there's more testing that can be done in addition to the standards-based conformance testing. There's two more sorts of testing here to discuss as well. So a key part, obviously, all of this testing is really trying to understand and build a connection with what the real experience is going to be in the field. So field-based testing is, if you like, the ultimate in terms of testing the experience of the phone, and in that respect, it's very useful. But it does have its issues. It's quite expensive. You've obviously got to find a network that's suitably mature that you can use it, and then you need equipment that you can drive around. And it's often also difficult to repeat the issues that you find with that testing when you get back in the lab. So you get some great data, and maybe you find some situations where the phone hasn't performed as you would like, but it becomes difficult for you to repeat that and then be able to work on it in a kind of robust way when you're back in the laboratory. So it's useful, but it sometimes is hard to take the learnings from that testing and apply it to your design. And then finally, quite a lot of design teams have proprietary test systems of their own. Typically what they may do is build a set of tests which they then grow and grow as they increase their learnings through their different design processes. So if they encounter, say, an issue with a particular element of the design, they might develop a test to look for that, and then keep that test and continually repeat that test with new designs as they develop more phones and do more projects. So this is a good way of capturing the learning that happens through the design process and for building a large suite for regression testing to help grow the robustness of your product. It does, however, require an investment in terms of setting up the infrastructure, and also an investment in terms of time for the staff who are going to keep that and maintain that going forward. So let's look now at the end-to-end IP as a measurement. So I think one of the nicest things about this measurement is it's pretty simple to do. Essentially, you're using the phone at the limits of its capability, but you're using the phone and testing whether or not it can support that limit that I just described. So you establish an end-to-end connection, you go for a maximum theoretical data throughput, and you test the phone against that parameter. And in doing that, you're typically stressing the phone because many elements of the phone's design have to work in cooperation to support that end-to-end theoretical limit. So it's a very good test at looking to see if you have some sort of a problem with your design. Maybe where end-to-end data throughput is not so strong is whilst it's good at finding a problem, it's not so good at isolating what your problem is. And that's really the motivation for today's topic, is to talk through end-to-end data throughput, peel back some complexity to help you with isolating problems if you find that you have an end-to-end data throughput measurement that's not as good as you were hoping for. One other point to say is that to the untutored user, the end-to-end data throughput test can create results that imply there's something the matter with the phone, where actually there's something the matter with the test setup. So that's another area that we'll talk about today, and is one to treat with caution. Okay, so let's move on now and start to work through this measurement and build up the complexity. So I won't talk about each of these now, because I'm going to introduce all of them as we work through. But essentially what I'm going to do here is I'm going to build up complexity from a very simple beginning, adding more and more complexity till we're ultimately in quite a real-world scenario doing throughput measurements with fading and so on. And then as we do that, we'll talk about the challenges associated with that complexity, and that will help in terms of being able to anticipate issues if you're doing measurements of data throughput yourself. So what's step one? Well, hopefully step one is one that appears in the market in the early days, but ultimately you start to not even think about it or worry about it. But at the very beginning, you certainly do need to worry about it. And the question here is, will my device actually connect to the base station emulator or to my network? And there's really three areas to this process of the connection. I'm showing them in these three vertical comments here. The first is that the UE needs to essentially have a receiver that can synchronize to the downlink from the base station and then decode the broadcast information about that cell so that it knows characteristics of the cell and is in a position to transmit back to the cell. So typically, the interface that you've got with the phone will share with you information about whether it's done this. You'll typically get bars appearing on the UI to indicate that you have been able to synchronize to the downlink and you're ready to make a connection. So after you've synchronized to the downlink, the next task is for the transmitter side of the UE to essentially tell the base station emulator that it exists. At the moment, the UE knows about the base station, but the base station doesn't yet know about the UE. So what happens is the UE transmits on what's known as a random access channel, sending information to alert the base station that it exists. And after that, the base station responds and tells the UE to adjust its powers and timing, and then the UE is able to essentially communicate with the base station. So that's our first uplink signal. And after that downlink-uplink exchange, we then move into a protocol scenario where we want to work through a number of different processes in order to get access to the network. We need to get through security. We need to exchange things about authentication, encryption. We need to get resources. We need to be given an IP address. We need to be given bearers with which to communicate. So all of these steps need to take place. And then the UE is connected to the network and is able to communicate with that network. Now, I did mention how hopefully this is complexity at the beginning of the technologies phase, and then it goes away. And whilst that is true, we do also see technology coming along all the time which adds complexity to this. So, for example, with LTE now, many of the phones will want to do a voice over LTE connection. And to do that, as part of their connection setup, they'll be looking to do an IMS registration, and they'll probably be looking to use IPv6 to do that. This will create new complexities in this space here. So you may find that a phone that used to connect stops connecting simply because it's not keeping up to date with the complexities that's expected as it tries to join the network. So what can you do if you're trying to troubleshoot in step one? Well, I guess there's two phases to that. The first, I think, is to say, am I actually able to sync to the downlink? So to look for the bars on the phone to see a recognition of a downlink, and if you don't get that, you really need to get an analyzer up against the equipment and check that you've got a signal coming at the right frequency for your downlink. Get back to the basics, basically. But if you can ascertain that you've definitely got a downlink you can synchronize to and there's transmissions on the uplink, then you've probably got a protocol problem. And then the best thing to do would be to take a protocol logging tool and log all of the messages during this exchange. You can then revisit each of those messages and find out at which point the phone or the base station emulator sent an incorrect symbol, or there was some mismatch in terms of expectations and the process came to a halt. And then that will have to get corrected in order for you to move on. Okay, let's assume we've managed that and we've moved on. So step two, what we need to do now is ensure that the UE has good quality uplink transmissions. Obviously, if we want to get very good very good end-to-end data throughput, then we need, we're testing primarily the downlink when we do that, but we do need a solid uplink as well. And so what we do here is, before we do end-to-end traffic, in a simpler test mode, we ask the UE to transmit on the uplink, and then we make parametric measurements on that UE to test that its signals are of a good quality. So we might test the power that we were expecting the UE to send. We might test that the EVM, the error vector magnitude of the signal for high-order modulation schemes, or test the EVM right at the band edge where we may see some distortion. We might look for spurs, both in-band and out-of-band, that might worry us. We might look for linearity issues, look for spectral regrowth as we adjust the powers. And then another thing we could do is start turning on and off other radios that are resident inside the UE to check there's no interference issues associated with other activities whilst we're using the radio that we're testing. So this is a 3GPP list for the transmitter measurements for LTE. So there's a whole variety of those, but they're kind of focused on what I've just said: power, EVM, spectral growth, that kind of thing. And this slide here shows a reflection or a measurements that have been taken for a number of those different parameters. We've got a constellation scheme, spectral emission mask for the uplink transmission. How does the EVM compare with the symbol across the the time period of the subframe. So assuming all of that's working well and we've got a good uplink, the next thing to test, I guess not too surprisingly, is the quality of our downlink. So what we want to do now is test the receiver's capability. So again, it's a test mode. We're not yet doing end-to-end, but what we'll do is we'll use the base station emulator to construct a variety of different signals with different modulation schemes and make sure that the receiver can accurately recover those signals. And we'll probably do that for both low powers at the sensitivity limit and also for high powers at the level of the level of the highest power the UE can receive, because sometimes there's distortion at higher powers that can also lead to error rates. So this next slide shows an example of such a measurement. So we've got an error rate here. The error rate's very low, so we can't really see that line. It's running a 0 line here. And then we're showing a measurement for throughput up here near 100 megabits per second. And the way this has been calculated, this is actually a MIMO connection. And so we've got two streams, and we're counting acknowledged packets on the downlink, negatively acknowledged and lost packets. And we're doing that for both RF1 or stream 1 and stream 2. And then overall, we're calculating our error rate and our throughput. Error rate in terms of packet loss and our throughput. Now this list here is the 3GPP list for the receiver measurements. So we talked about the sensitivity and the maximum input level. You could also do testing to see how strong your receiver is to potentially blocking signals in band, out of band, spurious performance, and so forth. Okay, so we've now ascertained that we've got a good transmitter on the uplink, we've got a good receiver on the downlink. Here's our first test that's actually doing end-to-end throughput. And what we're starting with is a UDP test. So that's a unidirectional datagram packets, I think it stands for. And the approach here is to flood data in one direction and not to send acknowledgements on the uplink. So this simplifies the test because we don't have a response required. We just send the data on the downlink, no acknowledgements on the uplink, so there's no flow control, there's no retransmissions, there's no complexity associated with any errors. We're simply using the channel to send data on the downlink. So I should say this is a test which does flood networks. So you should do this test on a private network, not on a shared LAN, because it would take over the LAN. But within a private network, it's very useful. You essentially use a utility to flood data down to the base station emulator, and then that data is sent to the UE, and what you measure at this end is the amount of packets that are acknowledged, and hence the level of data or the throughput for the data that actually receives to the UE itself. It's quite straightforward to do. The lack of protocol in terms of flow control, error correction, retransmissions, the removal for all of that means that the results are relatively straightforward to acquire, and you get a very strong measurement of IP data throughput. So here you can see for this case, there was 102 megabits per second of raw bandwidth being applied to the base station emulator, and actually 99.9 have made it through to the device at the end. So we've had a very good connection here from a throughput perspective. So this is our first end-to-end test, and we've achieved a good UDP throughput. I'm just showing a graph here for how that might look if you were to, say, measure throughput versus modulation encoding scheme. So this is showing from 5 through to 27. 5 is a QPSK scheme with a given coding rate, and then by 27 we're up to 64 QAM. And we can see that there's a theoretical limit for data rate that's written within the standard, and our measurement at the MAC level sits exactly on that theoretical limit. What we measure for UDP throughput is a little bit below that, and that's because of the overhead associated with the IP traffic that's being sent. There's various address information and so on, which means not all of the packet is being used for data. Okay, so we've done an end-to-end with UDP, but we're continuing to add complexity. And the next stop is to move from UDP to FTP. And this is quite a significant change. In UDP, we had unacknowledged with no higher level ACKs or NACKs, and no need for error retransmissions or flow control complexity, so we weren't really very susceptible to any latency issues. That was a very good test for testing the overall throughput of that downlink, but it's not a protocol that is really used by many applications, such as file transfer and so on. It's used for sometimes for sending a video style application, but it wouldn't be used for transferring files or information. So it's not the full story in terms of protocol complexity, whereas TCP is a more complex protocol which is commonly used by different applications. So it's worth testing with TCP because that is simulating more of a real-world situation, and it does allow you to, say, do an FTP test, transfer files across, and time how long it takes for files to move across the network. However, when we shift to TCP, we are adding some complexity. TCP does do flow control. It have higher level acknowledgements and seek retransmissions for data that's arrived incorrectly. And also, the control algorithms for TCP are quite sensitive to different parameters, and they can impact your measurement. I'm going to go on to talk about that in the next couple of slides. So it adds complexity, which is good because it's used in the real world, but we also need to think about that complexity because it might impact the results we get for our measurement. Okay, so here's an example of a TCP measurement. It's exactly the same setup, but now we're using different protocol. We've got the TCP protocol, we're using an FTP server, and we're sending data across. And now we do have acknowledgements going back, the IP layer. We've always had acknowledgements at the radio layer, but now we have them at the IP layer, and that's going to impact retransmissions and flow control algorithms inside our TCP implementations. So maybe just to say a little bit about that. So TCP is a protocol that was developed long before there was thought of using wireless to send IP packets around the space. And so it has built into it an implicit understanding that if it sees a request for a retransmission, then that's the result of a collision in the protocol around accessing the media rather than actually an error, say, as you might expect to see across a radio network. So TCP sees the request for retransmission as something that tells the TCP algorithm that the network is congested, and so its behavior is then to back off the flow control to reduce the throughput because there's too many people trying to use the network. That's not actually the behavior we want in radio, because all we've done is lose the packet because we've got a lossy channel and we want to keep sending data because the channel's got better again, and now we need to make use of the propagation characteristics. So we need to deal with that, and the way that happens in the radio is we try as much as possible to hide TCP from seeing those errors so that the TCP doesn't use its flow control and back off. And then within the TCP itself, we want settings that mean that TCP doesn't have as much memory as it normally would have, so that it doesn't, because typically what TCP does, if it sees a couple of congestions, it thinks, oh, there's a lot of people trying to access this network, I'll back off quite a bit. So we need to make the window size small so that the TCP algorithm is able to react quickly and quickly return to full rate. Now, Marv will talk about this more in his case when he talks about the examples, but here's one that I've stolen from him just to show this point. So we can see here the over-the-air rate in the blue line, and then we can see the TCP rate in the magenta line. And in many cases, they just work together, and you see the overhead associated with the IP traffic. But you can see in one case here, this has been 10 FTPs, in one case with this ramping effect on a reduced throughput. And the reason for that is because the TCP has interpreted a packet loss as congestion, and it's ramping its flow control. It's something often referred to as TCP flapping. So we need to be careful to make sure that we try and avoid seeing that as much as possible, because that's reducing our throughput because of the TCP algorithm and not because of the radio. Okay, so that was adding TCP. Now we're going to move on and add additional bits of complexity. So in this case, we're adding support for applications. So this isn't really adding much complexity, but sometimes it's nice to look at the real application, to demo the real application, and then look at the statistics for what's happening with the IP traffic and the throughput requirements for that given application. Now, in this next case, we are starting to add some complexity that gets us nearer to the real world. Here what we're doing is adding either noise or adding a channel emulator, or both, to reflect what's happening in the real world. So we have two sorts of noise, additive white Gaussian noise, or in LTE world, we might want to add OFDMA channel noise, which is a specific for an OFDMA system. Each of these would impact the signal-to-noise ratio, which would clearly impact the throughput. Or we could add a channel emulator that would create the real world, or an emulation of the real world channel, and would also cause the propagation characteristics to degrade and therefore impact throughput as we're doing the measurement. With this one, we do need to take care, because if we cause long dropouts, then we'll come back to that TCP issue, and we'll be seeing flow control issues as we try and increase our throughput. Number 8 here is about whether or not it's robust. Lots of folks make end-to-end IP measurements, and in many cases, what they also try and do is they take those measurements over a long period of time to test whether or not their UE has any issues in terms of its robustness for carrying out many multiple processes in parallel. So if you let this test run overnight, you're certainly going to introduce thermal effects. It's a test that makes the phone very busy, so things are going to warm up. And then if the way you've designed your memory architecture has any issues, as you do run the test for a very long time, you will find about any memory overflow issues or memory leakage problems that may arise, which are going to give rise to changes of throughput as the test progresses. So it's a good way of doing a long test, overnight style test, and testing the robustness of your design. People sometimes do this and then do SMS and voice parallel with that, just to continue that problem. Okay, this next one is saying more of the real world stuff. We're adding channel emulation, and this time we're even going to add the feedback that happens in the real world. So now the phone is responding to the quality of the channel, and it's giving information back to the base station, and the base station's adjusting its characteristics for the downlink signal. So this is actually probably going to help the test, because this will remove the long periods of poor connections, because the base station will deliberately make the modulation scheme simpler when the channel becomes weaker. And then finally, we can take all of the setups that we've been talking about and then add on top of that battery life to repeat doing these different processes, end-to-end throughput, different services, different levels of complexity, and then whilst doing that, also measure battery life on top of that. And we do that by having a power supply which feeds the UE, and then we're able to control that through a SCPI interface and take measurements of current during the levels of activity. Okay, so hopefully you've seen there that we can add levels of complexity to build up the overall data throughput measurement. And the most complex measurement is a very demanding measurement for the phone, but it is quite tricky to troubleshoot. Although the way to do it is to be able to peel it back to levels of simplicity that make it easier to see what's going on. So I'm going to hand over to Marv Wagner now, who's our applications expert. He does lots of IP throughput measurements, and he's going to talk about and show you some measurements he's made for real commercial devices over the years.
Okay, this is Marv, and I want to thank Mike for that presentation and developing this whole 10-step program, because I realized after he put this together that I am a data throughput junkie, and I really need the 10-step program trying to overcome this. So here's just a few of the things that I've discovered over time that we find pretty useful when measuring throughput. And a lot of these measurements are done with HSPA and HSPA plus devices. They've been around the longest, and I've had the most experience with those. The concepts are the same, whether you're doing LTE or HSPA or HSPA plus. So this first slide shows repeatability. And in order to get repeatable results, you need not only stable test equipment, but also some software that can exercise things in a consistent way. So what we have here is we have an automated system. It's called Interactive Functional Test, or IFT, and we're able to set up a data modem and then make repeated measurements. And you can see that each one of these runs took about 450 seconds, so roughly 10 minutes. And I can just do it over and over again, and then we have a comparison tool. You can lay them on top of each other. Now the test itself, we do all forms of throughput. We do downlink only using UDP, and then we do uplink only. Let's see, I think I have to turn on the, you can't see my mouse, can you? There we go. Okay, so downlink UDP. And then we go to strictly uplink UDP, and we do both of those together simultaneously. And then we turn around and do the same thing for FTP. So what do we see here? Very consistent, easy to get consistent results with downlink FTP, UDP, and every time we get the same throughput results. So all those traces are just jammed on top of each other, very close comparison. Also, when we do the uplink, we see a phenomenon that I've called uplink overflooding, where if you're trying to send UDP data at a level that's too high for the channel you have, sometimes the device and the drivers for the device will do something analogous to this FTP flapping we've talked about, similar kind of things where they kind of push back and this data flow will stop momentarily. And you can see that all of these runs, and I think we have 23 of these on top of each other, were very consistent for the first few seconds, nothing happened, and then you start to have this bounce back issue associated with it. Also, when we look at the simultaneous flood, there's an issue associated with the uplink, very consistent again with in terms of time with all these runs. Now we'll turn to the FTP and look at this TCP flapping. And as Mike has explained, when you have lost packets, the TCP stack goes into what I call a panic condition, where it says, oh my goodness, we've got problems. We better slow down our rate. And it goes almost to zero. And you can see this, the data rate over time just drops very low, and then it slowly comes back over time. And when we ran this particular device, we ran it 23 times. We only saw that flap twice. Also, when we're doing the simultaneous UDP, simultaneous FTP, where we've got uplink and downlink going, it's very hard to get the same results we get for solo uplink or downlink because of the conflict in the opposing channel, where you've got the AX and NAX that need to get through quickly to keep your, say, the uplink is trying to do an FTP, so you've got the AX and NAX coming on the downlink. If they don't get there in time, you'll stall the stack, and data will stop flowing. Same thing going the other direction. So systems really need to be made with kind of a fast-track channel for the AX and NAX to get past all the data in the opposing channel. And in this case, that hadn't been implemented, so the effective rate when we do simultaneous is reduced quite a bit and a lot noisier. Okay, the next thing we want to talk about is device performance. And you're trying to pack a lot of computing power and RF processing power into small devices where power consumption is an issue, and sometimes you're not able to put the processing power you really need in there to handle things at full rates. So for this one, we're going to go way back to, I think this is a category 6 or category 8 HSDPA device. So it's 7.2 megabit maximum. If we run the downlink with a large packet size for our RLC packets at 656 bits, we are able to get very close to the theoretical limit. Theoretical limit for the over-the-air is 7.2, 6.7 for IP because of the overhead associated with IP packets. You need to keep track of, you know, where do they go into, and do I need to retransmit them and all that sort of thing. However, if we make it a smaller packet size, and that's the only thing we change, the average throughput drops from 6.3 to 3.98, or approximately 4. So we only get about 2/3 the throughput, and this is strictly a MIPS issue with the device under test. And you'll see this especially with devices that are fairly new in a given technology. You'll see these MIPS limitations limiting the throughput. So we show this. This is just a close-up of the average, and this is a throughput monitor shown from the front panel of our instrument showing UDP alone, FDP. And here when we do the FDP with the 336 PDU, that's the rate we see. Consistent difference between over-the-air and the IP rates, however, much lower, approximately 4 megabits per second, whereas when we use a larger PDU size, we get closer to the 6.3. Okay, so that's showing some MIPS limitations, and one of the things you can see as you peel the onion back. Continuing on that theme of devices get better over time, I have 3 different devices from 3 different manufacturers, and this is now being done at HSDPA plus category 14 or 21 megabits per second. All the first generation devices from a given manufacturer, the throughput is shown in red. And here what we've done is we've changed the test block index size, which in effect is like changing, well, the size of the package to transcend each TTI. So down at 50, your throughput is around 15 or 17 megabits per second. First and second generation devices both perform the same. However, as you increase that packet size, getting close to the maximum throughput, you'll notice that first generation devices have some issues. From manufacturers 2 and 3, things just really start to fall off after TBI 58 or approximately 19 megabits per second, and so you have a real tough time, and you're not able to achieve the maximum throughput which you expect at 21 megabits per second. Manufacturer 3, actually, their device was a little better in that it just had a problem at this one block size, TBI 61. And in fact, even the second generation devices have some issues. You kind of expect this to be a nice flat line as you change the block size, but all of the devices come up very close to the theoretical limit when we get close to the max packet size. Okay, now he seems to have lost my cursor. I'm going back. Okay. So that's second time around. Second generation devices in a given technology are usually much closer and higher performance, closer to the theoretical limits. Seen this consistently, you know, as we move from category 6 at 3.6 megabits per second to category 7, category 8 at 7.2, and so on. And what you find is, if you do a device that's, say, the 21 megabits per second, it'll run 7.2 right at the theoretical limits. So as they've increased the processing power and the capabilities of that device, it's very easy to look at, max rates at the previous speed, but not necessarily the current. Okay, now I want to talk about another thing that can get in the way of making these measurements, and that's diversity. Diversity in the real world is a very good thing because it allows you to take multipaths, and through the power of all these digital modulation schemes and decoding and soft combining of bits, you're able to get better performance. However, in a test environment, that can get in your way. So in the upper left here, we show a plot we've made where we measure throughput on a given device, and we're changing the RF power here, and we actually go from a high power to a low power. So if we start at the real high powers, you see the throughput is pretty consistent. Each one of these little vertical lines is where we started a new FTP. And we get towards the sensitivity limit of the phone because of digital modulation. It hangs in there quite well, and then it falls apart over a very short RF range. Now, when we go to measure another device, in fact, this is the exact same device on the upper left. On the lower right, what we've done, this device happens to have 2 RF connectors, which is pretty uncommon, but allows us to make some consistent measurements, whereas if you only have one RF connector, whether diversity is turned on or off will affect this, and that can be a little harder to troubleshoot. So if we just leave that second antenna port floating, sometimes it tries to combine the information and does a good job, and other times it's just horrible. So you'll see the effective throughput can drop by a factor of 3 due to incorrect combining of RF signals, and really the expectation with diversity is you get the same RF level, but maybe you get some reflections, some extra delay, and when it's trying to combine leakage with a real strong signal on the other, it can be disastrous. So same RF conditions, other than the fact we haven't terminated the second RF connector, and you can see that the throughput versus RF power is really messy. And so this becomes very hard to get consistent results if you haven't properly taken care of the RF characteristics and taken care of that second port and terminated that. I believe the next slide we show here, this is that same lower right from the previous slide where we show a device with 2 RF connectors, one of them with the proper signal, the other left floating. And down below we show similar kind of performance for a device that only has 1 RF connector. So in this case, there's really, short of getting commands from the manufacturer to disable diversity inside the device, there's nothing you can do. And we see the same kind of drop in RF and throughput because of this incorrect handling of diversity in this range, whereas down in the lower levels it actually works much better. Same idea though, diversity can get in the way in the lab. Okay, back to the idea that not all devices are created equal. This is just a way to show that we've done some measurements and been able to look at significant differences in performance based on 2 devices of the same vintage. This was actually done quite a while ago when we were measuring category 6 devices where 3.6 megabits per second is the over-the-air rate and lower for Keysight IP rate. And in this case, the way we've used Excel to plot this data, we actually end up with the high power minus 40 dBm on the right and the low power on the left. So it's a little bit of a mirror image of the last thing I showed you where we looked at it versus time. This is versus RF power. So in this case, this device, pretty flat overall RF powers until we get down to the sensitivity. You got a few of these little downward spikes, and that's that TCP flap thing we talked about. And we show, here's one where we happen to have a flap at that particular power. And these flaps are very hard to eliminate. and can make testing of IP with TCP very difficult, which is one of the reasons why if you use UDP, you don't deal with this. But once again, if you want to measure the entire system, it's good to measure TCP. Just be careful that the effects of this flapping are not introduced by your test system versus the DUT, the device you're trying to test. Early on, we had a real issue with TCP window size because you have to make that quite large. When you have large data rates, you have long latency, you have to have a big buffer. And if you don't have that, you start to limit the flow based on your window size. And that doesn't look like a flap. That's more of just the over-the-air and the IP rates both being much lower and noisier. Okay, so let's compare this device, which is actually a pretty good one, now to one that's not so good. So this is, again, a first-generation Cat 6 device. You'll see the throughput where we were getting close to 3.3, I think, was the IP rate. Here, the average is more along the lines of 2. And this one, we've measured a whole bunch of different frequencies. Those are all the RF channels for the UMTS band 1. And you'll see that occasionally you get something that looks pretty good. Here's one we didn't have any dropouts, and that corresponds to a pretty high rate. But by and large, this device just did not perform very well. So there is a difference between whether this is an RF issue or a coding issue inside the device. It's a little hard to tell, but we can tell the device does not perform as well as it should. And here we have a composite just showing the device that did well, device 1, and the device that didn't do so well, device 2. Okay, we've showed a couple of the graphs now where we plot throughput versus RF level. And from a kind of a classic theoretical perspective, you'd expect this to be nice and flat at all high powers for RF. And then when you start to hit that sensitivity point and the coding falls apart, it drops quite rapidly. Also, we've seen there are some plateaus you hit on the way down, and that's kind of the classic look. One of the devices we tested, and this is actually 2 different RF channels, the same device. So channel 10562 is a band edge. And for some reason, this device, it has some sort of compression or interference or intermod inside the device, where when you increase the RF power, the data throughput is actually lower at that particular channel, whereas at other channels, it's nice and high all the way up to the highest power that the device will accept. Okay, more of the same device. This is the channel that drops off, and you can see here's all of the RF channels from the high band to the low band. You can see this sensitivity point is pretty consistent across all those RF powers, which says that device is pretty well calibrated so that all your RF performance across the frequency band works very well, except for this one band edge that we've discovered. Okay, another phone. We didn't have problems at the high end, nice and high for everything, but this one, another one of the band edges, this happens to be the high band, 10838, and you'll see that it's got an RF problem where the sensitivity point is almost 15 dB higher at that band edge. So probably something in the RF calibration of the phone. Okay, at this point I'm going to turn it back to Mike to do a summary.
Thank you very much, Marv. So hopefully you've seen how end-to-end IP data throughput is a very useful measurement which stresses the device and tests it at the limit of its specification across many parts of its implementation. So it's a good measurement for finding problems. But I think it's we've hopefully also shown you that sometimes it's hard to track down where those problems are happening. If you think about it in terms of a model and building up complexity, it becomes maybe a little bit easier to consider where those problems will be. And thanks to Marv there, we've just looked at some real-world issues with commercial devices and seen how those problems definitely do exist, and measuring them and working on them can highlight some issues with your devices. So thank you very much for your attention, and I hope you found today's presentation helpful.
Thank you, Mike, and thank you, Marv. Thanks a lot for these presentations. We have just reached the top of the hour, and we have made it in time. Also, we wanted to give you some time of question and answer. While both Marv and Mike were speaking, we just received only a few questions, so both went deep into the technology. So, however, if you have questions after these presentations, or if you think you would like to have more information, please contact us. We are happy to help you out. And as I said, we are at the top of the hour. We will close this session in a moment, but I would like to remind you, you will see after this session an evaluation form popping up on your screen, and we appreciate your feedback on the seminar by filling out this form. So now we are done. Thank you again for your attendance. So we wish you all a nice continuation.